Hello viewers, welcome to this exciting video. In this video, we will be looking at the November 2020 Science Paper 1, question B4. Question B4 reads, Figure B4.1 below is a diagram showing a stone of mass 2 kilograms that was pushed up a slope from Q to R. Figure B4.1 below is a diagram showing a stone of mass 2 kilograms that was pushed up a slope from Q to R. All right, so the stone was pushed from Q, which is this point, up the slope to R, which is this point, which is the topmost of the slope. All right. And the stone had a mass of 2 kilograms. Okay, so we need to bear that in mind. And on the side, we have a point S, which the paper is saying is the midpoint. So meaning it is halfway. So the distance from S to T is equal to the distance from S to R. So that is that. So 75 joules of work was done in moving the stone up the slope from Q to R. 72 joules of work was done in moving the stone up the slope from Q to R. A. What is the potential energy of the stone at R? All right. Now, for this question, people may try to think too much and bring in all what they can come up with. For example, one of the things I have seen people saying is that, all right, if this stone was pushed up this, it means that the work done should consider the distance from Q to R through the slope. All right, which to some extent you may say it may be true. You may be tempted to say it may be true, but remember, it is the work done in moving the stone, not the work done by whatever force that was moving the stone. If a force was pushing this stone, if the stone was here, and the force was pushing it in this direction, it means that the work done by the force F in moving the stone will be, the force will cover a distance from here up to here. So this will be our distance, okay? And in doing that, we'll bring in aspects of friction and whatever and whatever. But the work done, okay, on the stone is just the gravitational potential energy, the gain in gravitational potential energy of the stone. Remember, gravitational potential energy is work against gravity. Work against gravity. No wonder it does not depend on the path taken, but only on the change in height. Okay, so let's be careful on that one. Okay, so the work that is being described here is work against gravity and not the work done by the force. If it was the work done by the force would have been mentioned in the question. All right, so we get rid of all that and we continue with ours. So the work done, we've said work done against gravity is the gravitational potential energy. And the question asks us, what is the potential energy? So if the work that was done in moving the stone up, okay, in moving the stone where? Up, okay, is 72 joules. It means that the gravitational potential energy is 72 joules. So that is the answer to A. Hence the K1 mark, meaning there isn't much work. Even the space for working is limited. 1 mark. All right. We proceed to B. B, if the stone falls through side RT, what would its potential energy be at S, the midpoint? Now, what happens when an object is falling is this. So at the top here, the gravitational potential energy or potential energy is at its maximum value, okay? While the kinetic energy is zero because it's not moving, all right? But once the stone starts falling down, gravitational potential energy starts reducing, and the reduction in gravitational potential energy becomes the gain in kinetic energy. So after the object has fallen halfway, it means that we have half of what we started with as potential energy. So the potential energy here at this point is equal to half of what we started with. Half of, so here allow me to put prime, okay, to indicate that it is potential energy at the midpoint. So it will be half of the potential energy that we started with, okay? So what is half of the potential energy that we started with? And the kinetic energy also here will be equal to half also of the potential energy that we started with, so that when we add the two, we get back what we started with, and in accordance with the law of conservation of energy. So let's continue. So if the potential energy there, okay, is half of what we started with, what is half of 72? So we are just going to say that for at this point, the potential energy is equal to 72 joules divided by 2, which is equal to 36 joules. So the potential energy there is 36 joules. So 36 joules. That is the potential energy at the midpoint. All right, let's proceed to C. C, calculate height TR. They want the height TR. So from T to R. So they want this height. All right, let's see. So we have been given the mass as 2 kilograms. Okay, we have been given the potential energy at the maximum point as 72 joules. Now they want us to find the height. So we know that the gravitational potential energy is equal to mgh. All right, and we've been given that the potential energy is 72 joules. That will be equal to the mass, which is 2 kilograms, multiplied by 10, which is the acceleration due to gravity, multiplied by h. So what we are going to have is 72 is equal to 2 times 10, 20. 20 times h, 20h, divide by 20, divide by 20. We cancel both sides. So 72 divided by 20. So 72 divided by 20. We have 3.6. 3.6. So our height is equal to 3.6 meters. So we now write it there, 3.6 meters. So that is the height TR. All right, we go to C2. C2, velocity of the stone just before it strikes the ground. So as we said, okay, so at this, when we are starting here, so the maximum potential energy here was 72 joules, okay, while kinetic energy was 0. Now at the bottom here, potential energy is at its minimum, which is equal to 0. while the kinetic energy is at its maximum, which is equal to 72 joules. So all the potential energy has been transferred to what? To kinetic energy. So we are going to use 72 as our kinetic energy just before it hits what? The ground, where height is equal to 0. So we now start. We know that kinetic energy is equal to half mv squared. So we have kinetic energy, which is 72 joules, is equal to half multiplied by the mass, which is 2 kilograms, multiplied by v squared. So 2 there and 2 there. So we have 1 multiplied by v squared. So we are going to have 72 is equal to v squared. So we are now going to say v is equal to the square root of 72. So v is equal to the square root of 72. So what is the square root of 72? So the square root of 72 is equal to 8.49. 8.49. So 8.49. So v is equal to 8.49 meters per second. So that is what we're going to write there, 8.49 meters per second. So that is the velocity. This brings us to the end of our video.